Presentation 1. PTSB and SS Activity Campaign. Annexer. Moments. Population parameters like mean and variance are called moments of the distribution. In this slide I define the moment and discuss the difference between central moment and moment about origin, also called raw moment. To find moments we can use four main techniques. Apply the definition of the moment directly. Probability generating function. Moment generating function. Characteristic function. Moments about origin. Definition. Moments about the origin, raw moments. The RTH moment about the origin of a random variable x, denoted by microsign 0r, is the expected value of xr. Symbolically, micro r equals exr equals xrf x 1 for r equals 0, 1, 2. When x is discrete and micro r equals exr equals infinity xrf x dx 2. When x is continuous, the RTH moment about the origin is only defined if xr exists. A moment about the origin is sometimes called a raw moment. Note that micro 1 equals x equals microsine x, the mean of the distribution of x, or simply the mean of x. The RTH moment is sometimes written as function of theta, where theta is a vector of parameters that characterize the distribution of x. If there is a sequence of random variables, x1, x2, xn, we will call the RTH population moment of the ith random variable microsine 0I, r, and define it as micro I, r equals xri, 3. Central moment. Definition. The RTH moment about the mean of a random variable x, denoted by microsine r, is the expected value of x, microsine x r. Symbolically, microsine r equals x, microsine x r, equals n area summation x, microsine x rf x 4, for r equals 0, 1, 2. When x is discrete and microsine r equals x, microsine x r, equals infinity x, microsine x rf x dx 5. When x is continuous, the RTH moment about the mean is only defined if x, microsine x r, exists. The RTH moment about the mean of a random variable x is sometimes called the RTH central moment of x. The RTH central moment of x about a is defined as x, ar. If a equals microsine x, we have the RTH central moment of x about microsine x. Microsine 1 equals x minus microsine x equals minus infinity x minus microsine x f x dx equals 0. Microsine 2 equals x minus microsine x 2 equals minus infinity x minus microsine x 2 f x dx equals vr x equals sigma 2, 6. Also note that all odd moments of x around its mean are 0 for symmetrical distributions, provided such moments exist. If there is a sequence of random variables, x1, x2, xn, we will call the RTH central population moment of the ith random variable microsine I, r, and define it as microsine I, r equals xi r, micro I, 1 r, 7. When the variables are identically distributed, we will drop the I subscript and write micro single quote r and microsine r. Video. Skewness. Basic theory. The skewness of x is the third moment of the standard score of x. Skew x equals 3. The distribution of x is said to be positively skewed. negatively skewed or unskewed depending on whether skew x is positive, negative, or zero. In the unimodal case, if the distribution is positively skewed, then the probability density function has a long tail to the right, and if the distribution is negatively skewed, then the probability density function has a long tail to the left. A symmetric distribution is unskewed. Suppose that the distribution of x is symmetric about a. That is, the distribution of a(x) is same as the distribution of x, a. Then, e(x) equals a. Skew x equals 0. Proof. We proved part A in the section of properties of expected value. Thus, skew x equals e3. Skew x can be expressed in terms of the first three moments of x. Skew x equals e(x3 minus 3 mu e(x2 plus 2 mu 3 sigma 3 equals e(x3 dash 3 mu sigma 2 dash mu 3 sigma 3. Proof. Note that, joking, mu 3 equals x3 minus 3x2 mu plus 3x mu 2 minus mu 3, joking. Mu 3 equals x3 dash 3x2 mu plus 3x mu 2 dash mu 3. From the linearity of expected value we have joking. Mu 3 equals e(x3 minus 3 mu e(x2 plus 3 mu 2 e(x minus mu 3 equals e(x3 minus 3 mu e(x2 plus 2 mu 3 joking. Mu 3 equals e(x3 minus 3 mu e(x2 plus 3 mu 2 e(x minus mu 3 equals e(x3 dash 3 mu e(x2 plus 2 mu 3. The second expression follows from substituting e(x2 equals sigma 2 plus mu 2 e(x2 equals sigma 2 plus mu 2. Since skewness is defined in terms of an odd power of the standard score, it's invariant under linear transformation with positive slope, a location scale transformation of the distribution. On the other hand, if the slope is negative, skewness changes sign. Suppose that a element of R element of R and B element of R 0. Then, skew a plus Vx equals skew x. Skew a plus Vx equals skew x. If B greater than 0, B greater than 0. Skew a plus Vx equals minus skew x. Skew a plus Vx equals skew x if B less than 0. Proof. Let z equals, joking, mu divided by sigma z equals, joking, mu slash sigma, the standard score of x. Recall from the section on variance that the standard score of a plus bx is z if b greater than 0 and is z if b less than 0. Recall that location scale transformations often arise when physical units are changed, such as inches to centimeters, or degrees Fahrenheit to degrees Celsius. Variance. Definition. As usual, we start with a random experiment with probability measure p on an underlying sample space. Suppose that x is a random variable for the experiment, taking values in f subset of or equal to r. Recall that the expected value or mean of x gives the center of the distribution of x. The variance of x is a measure of the spread of the distribution about the mean and is defined by var x equals x, x2. Suppose that x is a discrete distribution with probability density function f. Use the change of variables theorem to show that var x equals n area summation x element of s x to f x 2. Suppose that x has a continuous distribution with probability density function f. Use the change of variables theorem to show that var x equals top half integral bottom half integral s x to f x dx. The standard deviation of x is the square root of the variance. It also measures dispersion about the mean, but has the same physical units as the variable x. SD x equals var square root x. Chebyshev's inequality. Basic theory. Chebyshev's inequality, named after Pafnuty Chebyshev, gives an upper bound on the probability that a random variable will be more than a specified distance from its mean. This is often useful in applied problems where the distribution is unknown, but the mean and variance are at least approximately known. In the following two exercises, suppose that x is a real minus-valued random variable with mean mu equals x and standard deviation sigma equals SD x. The usefulness of the Chebyshev inequality comes from the fact that it holds for any distribution, assuming only that the mean and variance exist. The trade-off is that for many specific distributions, the Chebyshev bound is rather crude. Note in particular that in the last exercise, the bound is useless when k less than or equal to 1, since 1 is an upper bound for the probability of any event. Credits.